Hi everyone, here we are going to see about the continuation of unit 1. Let me see one by one. So here is the one of the challenge, that is consider the analog signal as xa of t and 3 cos 10 180. We have to determine the minimum sampling required to avoid the aliasing. Then we have to find the Nyquist rate and Nyquist interval. So find the folding frequency also. So this is the problem. So here we are going to find out. First we have to write out the analog signal, that is xa of t, that is 3 cos 10 100 t 100 pi t. So the general equation will be x of t is equal to a cos omega t. So compare these two equations. So for a the value is 3 and for omega the value is 100 pi. Okay. So first thing will be we have to determine the minimum sampling rate required to avoid the aliasing. So that is fs is greater than or equal to 2w. So 2 pi f is equal to omega, that is equal to 100 pi. So from this we have to find out the f value, frequency value, that is 50. This is the maximum frequency. Omega is equal to 50. So the minimum sampling rate will be fs is equal to 2 omega. So that is 2 into 50, that is 100 hertz. Okay. Next question will be to find the Nyquist rate and Nyquist interval. So the Nyquist rate formula will be 2 omega. So that is 2 into 50, that is 100 hertz. Nyquist interval is 1 by 2 omega, that is 1 by 2 into 50, that is equal to 1 by 100 seconds. So find the folding frequency is third one, that is fs by 2. So sampling frequency by 2, that is 100 by 2 is equal to 50 hertz. So half of the sampling frequency is 50 hertz. So next we are going to see about the discrete time signals, that is the representation of discrete time signals, elementary of discrete time signals, classification of discrete time signals and operation of signals. Then first thing will be the representation of discrete time signals. For this we have to going to see about the explanations. So there are different types of representation of discrete time signals. The first thing will be the graphical representation, functional representation, tabular representation and sequential representation. Okay. So that is x of n is equal to 1 for n is equal to minus 1 and 2 for n is equal to 0.1 and 0.5 for n is equal to 2, 1.5 for n is equal to 3 and 0 otherwise. So the tabular representation will be from the discrete time signals that can also be represented as n and x of n. So here we have to divided it as a minus 1, 0, 1, 2, 3. So for minus 1 that is 1, 2, 2, 0.5, 1.5. Okay. So sequence representation. So the finite duration sequence with the time origin, that is n is equal to 0, which will be indicated by the symbol. It is represented as x of n is 1, 2, 2, 0, 0.5, 1.5. So in this the arrow mark will represent the point. So that will be symbolized the point. So the infinite duration sequence can be represented as likewise. So finite duration sequence that satisfies the condition x of n is equal to 0 for n is less than 0 can be represented as x of n is equal to 2, 4, 6, 8 minus 3. So this will be the discrete time. So next we have representation. Next we are going to see about the elementary of discrete time signal. So in this there are different types of elementary of discrete time signals. The first thing will be the unit step sequence, second is unit ramp sequence, third is unit sample sequence, fourth is exponential sequence, fifth is sinusoidal sequence and sixth is a complex exponential sequence. So unit step sequence. The unit step sequence is defined as u of n is equal to 1 for n is greater than or equal to 0 and 0 for n is less than 0. So the graphical representation of u of n is shown in the figure. Okay. So next unit ramp sequence. So the unit ramp sequence is defined as r of n is equal to n for n is greater than or equal to 0 and 0 for n is less than 0. So the graphical representation of r of n is shown in the figure as likewise. So the next thing will be the unit sample sequence, that is unit impulse sequence. The unit sample sequence is defined as del of n is equal to 1 for n is equal to 0 and 0 for n is not equal to 0. So the graphical representation of del of n is shown in the figure. So the unit impulse function that has been the following properties, that is del of n is equal to u of n minus u of n minus 1. So u of n is equal to summation k equal to minus infinity to n del of k. Another thing is summation n equal to minus infinity to infinity x of n into del of n minus n naught is equal to x of n naught. Next thing will be the exponential sequence. So the exponential signal is the form of x of n is equal to a power n for all n. So the different types of discrete time exponential signals, when the value of the a is greater than 1, the sequence will be exponential. When value is of 0 less than a less than 1, it will be decay exponential. When a is less than 0 means it will be the discrete time exponential signals. Okay. Sinusoidal signal. The discrete time sinusoidal signal, which is given by x of n is equal to a cos of omega n plus phi, where omega n is the frequency and phi is the phase. Using the Euler's identity, we can write it as a cos omega naught n plus phi is equal to a by 2 e to the power of j phi e to the power of j omega naught n plus a by 2 e power minus j phi e to the power of minus j omega naught n. So since modulus of e power j omega naught n phi, the whole square is equal to 1. So that means the average power signal will be 1. Next is the complex exponential signal. So the discrete time complex exponential signal will be given by x of n is equal to a to the power of n e to the power of j omega naught n plus phi. So that is a power n cos omega naught n plus phi plus j a power n sin omega naught n plus phi. Okay. So next thing will be the classification of discrete time signals. There are 4 different types of classification: energy signals and power signal, periodic and aperiodic, symmetric and anti-symmetric, that is even and odd signals will be defined, and casual and non-casual. So first thing will be the energy signal and power signal. So energy signal means that is the discrete time signal. X of n in the energy is defined as E is equal to summation n equal to minus infinity to infinity modulus x of n the whole square. Next thing will be the power signal. So that is the average powers of the discrete time signal, that will be P is equal to limit n tends to infinity 1 by 2 n plus 1, that is summation n is equal to minus n to n modulus of x of n the whole square. So here the energy signal P is equal to 0, that is it is finite means. If the signal is finite and the average power of the signal is finite means the power signal will be E is equal to infinity. So here we are going to see one challenge, that is determine the values of the power and energy of the following signals. Find whether the signals are power, energy or either energy nor power signals. So first question will be x of n is equal to 1 by 3 the whole power n into u of n. Second will be x of n is equal to e to the power of j into pi by 2 n plus pi by 4. So first we are going to see solve it. That is signal x of n is equal to 1 by 3 whole power n u of n. So to find the energy signal, the formula will be E is equal to summation n equal to minus infinity modulus x of n in the whole square. So for x of n we have to substitute 1 by 3 the whole power n the whole square into u of n. So that is summation n equal to 0 to infinity 1 by 3 the whole power n into the whole square. So u of n is equal to 1 for n is greater than or equal to 0 and 0 for n is less than 0. So that is 1 plus a squared is infinity is equal to 1 by 1 minus a. So we have to 1 by 9 the whole squared. So we write this as 1 by 1 minus a formula. So that is 1 by 1 minus 9, that is 9 by 8. Next is find the power. So P is equal to limit n tends to infinity 1 by 2 power 2 n plus 1 summation n is equal to minus into n modulus of x of n the whole square. So for x of n we have to substitute 1 by 3. So after that we will get limit 1 by 2 n plus 1 summation n equal to 0 to n 1 by 9 the whole square. So limit 1 by 2 n plus 1, this will be written as 1 minus 1 by n 9 the whole power n plus 1 by 1 minus 1 by 9. So that is 0. So the energy is finite and power is 0. So the signal is an energy signal. Okay. So next question will be the x of n is equal to e to the power of j pi by 2n plus pi by 4. So here we have to substitute this in to find the energy. E is equal to summation n equal to minus infinity modulus x of n square. So next summation n equal to minus infinity e to the power of j pi by 2n plus pi by 4 the whole square into u of n. So that is e to the power of j of omega will be 1. So upper the whole term will be 1. So that is infinity. Next we have to find out the power. So that is p is equal to limit n tends to infinity 1 by 2n plus 1 summation n equal to minus n to n modulus x of n the whole square. So that is we have to substitute the e power j pi by 2n plus pi by 4 the whole square. So that will be the 1. So it will be written as 2n plus 1. So that is 1. Okay. So the energy is infinite and power is finite. Therefore the signal is power signal. Okay. Next. Periodic and aperiodic signals. So here is one of the problem, that is first thing the given signal is x of n is equal to e to the power of j 6 pi that is into omega naught. So that is omega naught value will be 6 pi. Okay. So the fundamental frequency of multiple pi will be n is equal to 2 pi by omega. So 2 pi by 6 pi. So that it will be cancelled. We will get n is equal to 3. So likewise second problem, x of n is equal to e to the power of j 3 by 5 into pi plus 1 by 2. Sorry, omega naught is equal to 3 by 5. So which is not a multiple of pi. So therefore the signal will be aperiodic. Okay. So next is symmetric and anti-symmetric signals. How we have to find out. So the discrete time signals is said to be symmetric. It satisfies the condition that is x of minus n is equal to x of n for all n. And next is xe of n is equal to 1 by 2 x of n plus x of minus n. For example, cos of omega n. Anti-symmetric means the signal is said to be odd signal and it satisfies the condition as x of minus n is equal to minus x of n for all n. So that is x naught of n is equal to 1 by 2 x of n minus x of minus n. So example is sine of omega n. Next we are going to see about the casual and non-casual. So that is the signal is said to be casual if the value of 0 for n is less than 0. Otherwise it will be a non-casual signal there. So for example, we have to signal processing a group of basic operations. So that will be represented as y of n is equal to t into x of n. So the basic set of operations are shifting, time reversal, time scaling, scalar multiplication, signal multiplier and signal addition. Okay. So first thing will be the shifting. So the shift operations will be takes the input sequence and it will shift the values by integer increment of the independent variables. So the shifting may be delay or advance the sequence. That is y of n is equal to x of n minus k, where n is the input and y of n is the output. If k is positive means the shifting will be delay. If k is negative means the shifting will be advance. Okay. For example, the signal x of n minus 3 is obtained by shifting means x of n will be right by 3 units of time. On the other hand, if the signal is x of n plus 2 means it will be obtained by shifting x of n left by 2 of times. Okay. So obtain the folding of the sequence by n is equal to 0 and it is denoted as x of minus n. Okay. Next thing, that is if the signal is x of minus n plus 2 and is x of minus n delayed by 2 units of time, and x of minus n minus 2 means that is x of minus n will be advanced by 2 of units of time. So the graphical representation will be represented in x of minus n minus 2 and x of minus n plus 2. So next thing will be the time scaling. So this will be accomplished by replacing n by lambda n and the sequence is x of n. So that is if L lambda is equal to 2 means we get a new sequence. So that is y of n is equal to x of 2n. So we can plot the sequence by substituting the different values. That is n is equal to minus 1, y of minus 1 is equal to x of minus 2 is equal to 3 and y of 0 x of 0 is equal to 5, y of 1 x of 2 is equal to 3 and y of 2 x of 4 is equal to 1. So next thing will be the scalar multiplication. That is here the signal x of n is multiplied by the scale factor as a. That is, for example, x of n is equal to 1, 2, 1 minus 1 means that is a is equal to 2. So signal will be a x of n is equal to 2, 4, 2 minus 2. Next is the signal multiplier. So that is the multiplication of the two sequences from another sequences. So there is we have to x1 of n and x2 of n. So we have to multiply these two values and get the answer. Okay. Next, addition operation means there is the two signals can be added by using the adder symbol. That is first the x1 of n will be given 1, 2, 3, 4 and x2 of n will be given 4, 3, 2, 1. So we have to add these two values. So we'll get the 5, 5, 5, 5. Okay. Next is the classification of discrete time systems. The discrete time system will be classified as static and dynamic system, casual and non-casual, linear and non-linear, time variant, time invariant, stable and unstable.